Hey guys, today we're going to do a little more practice on Newton's gravity and the inverse square law. Last time we introduced both of those at the same time, so today we're going to do more practice on that. So first we're going to practice Newton's gravity, then more about that. So let's go to practicing Newton's gravity first. I'm going to work through a problem with you, a couple problems here with you that are slightly more complex than the ones you did last time, but I think you'll be able to handle them. So let's go to the document camera here, and what we're going to do is we're going to figure out the gravitational force between a 100 kilogram physics teacher and a 50 kilogram student with a social distancing of 2 meters. So we want to know the gravitational force between these two objects, 100 kilograms and 50 kilograms, 2 meters apart. Okay, so we're going to use Newton's law of gravity, which is the force of gravity equals big G times m1 m2 over r squared. Big G is 6.67 times 10 to the minus 11th. We have that written up here for easy reference. We're going to do the two masses, which is going to be 100 kilograms and 50 kilograms. And we're going to divide the whole thing by 2 meters. But remember, we have to square that. Okay? Now, as I said last time, the hardest part of this is making your calculator spit out the right answers. So I'm going to work through this with my calculator here so that we can see how it progresses. Okay? So we're going to do 6.67 and exponent 11 change sign. So we're putting in the first number here, 6.67 times 10 to the minus 11. We're going to multiply that by 100. And what I recommend is you hit equals after each step, and then so that your calculator has finished what you want it to finish at each time. So I'm going to say equals. Then we're going to multiply that by 50 equals, and then we're going to divide that by 2 squared. Okay, so I hit x squared for the 2 and then set equals. And we get 8.3 times 10. We're going to count zeros here because we want to see how far we have to move the decimal point. So 1, 2, 3, 4, 5, 6, 7, 8. So 10 to the minus 8th newtons. That's the answer. 8.3 times 10 to the minus 8th newtons. Okay, 6.67 exponent 11 change sign times 100 times 50 divided by 4 equals, and we get 8.3 times 10 to the minus 8th. Okay. Yeah, so that's for like the force between two people. Now we're going to do another one where we're going to figure out the gravitational force between the moon and the sun. All right, so same formula here is going to be 6.67, so F sub G equals 6.67 times 10 to the minus 11th. Now we need the mass of the moon, which is 7.4 times 10 to the 22nd kilograms, times the mass of the sun, which is 2.0 times 10 to the 30th kilograms. The sun is way, way bigger than the moon. And we're going to divide that by the distance between them, 1.5 times 10 to the 11th meters, and we have to square that quantity. Okay? So here's how we run it. We do 6.67 exponent 11 change sign, 6.67 times 10 to the minus 11th times 7.4 exponent 22 times 2 exponent 30 equals, and we're going to divide all that by 1.5 times 10 to the 11th quantity squared equals, and we get 4.39 times 10 to the 20th newtons. That's the answer. Okay, now on my calculator and on most calculators, you have this little EE key, and that is a shortcut for exponents, 10 to some power. So I say 5, and I want to make it 5 times 10 to the 6th, for example. I just hit EE 6th. and that's put it. And most calculators have that, and that's an easy way to enter an exponent into your calculator. If you start going 5 times 10 to the sum raised some power of 6, then it starts to get very confused. A common error that calculators make, and I want to stress that this is an error that calculators make, not students, is when you put in the 1.5 times 10 to the 11th and then square it, sometimes the calculator will square the 11 instead of squaring the whole number. So it'll give you 1.5 times 10 to the 121st power, and that's not what you're looking for. Okay, so make sure when you do this that your calculator is not confused about what number you're trying to put in. Okay, so I walked through a couple examples here very quickly. My intention is that you can pause the video on the intermediate steps and make sure that you can get to these results. That's something you have to be able to do, and you just have to kind of figure out how you can make your calculator do it. Okay, that's a little bit on Newton's gravity, practicing that. Now let's go back to this here. Now we're going to talk briefly about the inverse square law. And we'll just go straight to the shortcut here, and then I'll explain why it is, because I'm not sure I'm going to have time to do it in this. So let's go back to the screen here. All right, what we're trying to do here is figure out the pattern of how the inverse square law works, how the force of gravity varies as you change the distance between two objects. So we're going to keep the masses the same, and big G, of course, never changes. So all we're going to be doing is changing the distance between them and seeing how that affects the force. Now we're going to assume that we've used numbers for the masses here, so all that equals 1. Okay, so big G times the two masses comes out to be 1, which means that F sub G is equal to 1 over R squared. Okay, now this is a method that you can use to construct a table that you can use to figure out how the forces change. That's what the goal of this is, because some students have trouble just plugging in numbers and seeing the math of it and all. So this is a table that you can construct and then draw answers from. So we're going to start off with a distance of 1, and we're going to say that the force of gravity between those two objects is also 1. So if the distance was 1, 1 over r squared would be 1 over 1 squared, which would be 1 divided by 1, which equals 1, right? So at a distance of 1, we're going to get a force of gravity of 1. Now, if we double the distance, we're going to square the 2 and flip it upside down. So 2 is going to go to 1/4. In other words, twice the distance is 1/4 the force. The way we get this is by saying 1 over 2 squared, which equals 1 over 4. So that's what it is. So if we double the distance, if we change the distance from 1 to 2, the force goes from 1 to 1/4. That's the inverse square relationship. If we go to 3, we square it and flip it upside down, we get 1/9 the force. If we quadruple it, we square it, which is 16, flip it upside down, we get 1/16 the force. And if we go 5 times the distance, we square it as 25, flip it upside down, 1/25 the force. That's the pattern that emerges from this. Okay, so that's what happens as you get farther away. Now, what happens when you get closer? And by the way, this part here is fairly easy to remember, and most students are able to remember this pattern when they need to. Now, working to shorter distances is a little tougher, but you can use this table to figure it out. Okay, so what happens if we go to 1/2 the distance? Oh boy, okay. The easiest way is to just look at an example that we already have. If we go from a distance of 2 to a distance of 1, we go from a force of 1/4 to a force of 1. So half the distance is 4 times the force, okay? Because 1 is 4 times as big as 1/4. Just like 4 quarters in a dollar. So when we go to cut the distance in half, the force goes up by a factor of 4. Now, what happens if we go to 1/3 the distance? Well, we look at the same thing. We go from 3 to 1, it becomes 9 times as strong. If we go to 1/4 the distance, it becomes 16 times as strong. If we go to 1/5 the distance, it goes 25 times as strong. Okay, now that's just based purely on the pattern here. We started with 1-to-1, we worked our way up to longer distances, and then we used these numbers to work backwards to shorter distances. Now you can also do it mathematically. So let's look at the 1/3 the distance. So the force of gravity is 1 over r squared. So that is 1 over 1/3 quantity squared. We have 1/3 the distance, so we're going to take 1/3 squared. So that is 1 over 1/3 times 1/3, which equals 1 divided by 1/9. And as you know, if you divide by a fraction, 1 divided by 1/9, that's the same as multiplying by the inverse. 1 times 9 over 1. So when we divide by this fraction, we can resolve that by flipping it upside down and multiplying by that. And 1 times 9 is 9. And that's the answer we get. So 1/3 the distance is 9 times the force. All right. This table, this method of creating this table when you need to answer questions on these works really well for a lot of students because it gets around having to do this weird math. If this confuses you or scares you, it's okay. You can still get where you need to be if you can remember how to create this table here, okay? The heart of it is this, and you use this to create this. And once you have the whole table, then you can answer questions about how things vary. Okay, now, it's useful here to know, let's go back to inverse square law. This is the summary of it. Why does this work? There's a worksheet that you have that explains this a little bit too. But the reason that Newton originally thought that the force would vary by the distance squared was because he looked at spheres and he looked at the geometry of spheres. It turns out that if you double the radius of a sphere, so if you start with a ping pong ball has a radius that's almost exactly 1/2 that of a baseball. And if you compare the surface area of these two spheres, the baseball has 4 times the surface area that the ping pong ball does. So if you double the radius of a sphere, you quadruple the surface area. And likewise, if you triple the diameter or the radius of a sphere, you increase the surface area by 9 times. The way Newton thought about this was that here's the Earth. It's producing gravity, but its gravity, the influence of it is kind of spread all over a sphere. And the farther away you get from the Earth, the larger that sphere is. And the gravity that it produces has to be spread all over the outside of that sphere. So Newton was thinking, if you double the distance between two objects, you're going to get 1/4 of the gravity. That made sense to me. Now, here's another way to look at it. I have this piece of paper here, which is 1/4 of a full sheet. Doesn't matter what's written on it, but it's 1/4 of a full sheet. Now, if I move the small sheet closer to the camera, I can make it look like they're the same size, right? And to do that, I have to put the small one half the distance that I put the large one. So the large one is twice as far away as the small one, but they look the same size because they cover the same amount of your field of vision. If you think of the camera lens as the center of a sphere that's looking out, toward me like a cone, if the surface of that sphere is 1 unit of distance away, a 1/4 sheet of paper covers, that much of it. This one is twice as far away and it covers the same distance, even though the actual piece of paper is 4 times as big. Okay. Their worksheet talks about a paint gun. The textbook talks about a butter gun and the idea of sending out a spray of material that will cover the inside of a sphere. And if you double the size of the sphere, the butter has to cover 4 times as much area, or the paint is going to be 1/4 the thickness. Okay. Anyway, so yeah, we've got some worksheets for you to do that are attached. But these examples that I've given you should be enough to